Okay, so I would like to start by thanking the organizers. Great pleasure to be here, my first time in the Hausdorff Institute. So let me start with my title. So the title is Additive Invariants of Orbifolds. So this is a joint work with Michel Vandelberg. So the workshop, it's about K-theory and number theory, if I remember correctly. So algebraic K-theory will fit here. I was not able to fit number theory here, so instead, I apologize for that. Instead, there will be things more non-commutative aspects, so hopefully still interesting for the audience. Okay, so maybe I would start with my motivation. So what is my motivation? So little k, it's a base field of arbitrary characteristic, and G, it's a finite group of order n, and always we will assume that the order of the group, it's invertible in the field. And now I have a scheme which is smooth, a smooth K scheme. And the group G is acting on X. So from there, I can consider the corresponding global orbifold. So the motivation is actually two formulas that I saw in the literature. So the first formula I saw, so I opened a paper of Vistoli, and in the second page, it's a paper from '91. So in the second page, there was a formula for the computation of the algebraic K-theory of the orbifold after inverting n. So in other words, for computing the G equivariant K-theory of X. And the formula is as follows. So it is a formula. So a formula which, when I saw it, I didn't know what these symbols meant. So later, I opened a different paper of, in the third page of Baranovsky from 2003. And there is a formula for computing the cyclical homology of the orbifold. And the formula is as follows. So it's again a direct sum. Okay, so now after looking at these two formulas, I observed that somehow they are describing the K-theory of the orbifold or the cyclical homology of the orbifold using just fixed point data. So if we think in the as Grothendieck, we can ask the following question: are 1 and 2 two shadows of a motivic formula? So it is really my motivation. So in particular, I would like to know, why does this work? What is really the ingredient at making these decompositions work? And I would like to understand, why is this formula simpler than this one? What's the difference, etc. So I would like to understand this in a conceptual viewpoint. So before, so also one of the goals of the talk is that now, when I saw the formulas, I didn't know what those things are. But by the end of the talk, I hope all the audience know. So it's also the so maybe remark about 1. So there are in this formula assumptions that K, our base field, contains the nth root of unity. So an arithmetic assumption. There is also the assumption that X carries an ample line bundle. And in what concerns 2, there is this assumption. It's like this, right? Okay. There is this assumption that X is quasi-projective. So I know that a lot of mathematicians here are allergic to this kind of condition. So also if we manage not only to solve this, but to remove this would be great. And now we try to look at the proof. So you look at the proof. The proof is evolved, and in particular uses this mysterious property called devisage. So devisage is something that we don't have for this kind of invariant. So I cannot just mimic this proof to recover this. So I'm going to look again now to the proof of this. And when you look at this proof, so this proof uses all the specificities of cyclic homology. So again, this proof is not helpful, because I cannot try to mimic this proof. So new ideas are needed. Okay, so this is my introduction. So now I want to explain the title. So I will start by explaining what are additive invariants. So I place myself in a very general setting. And try to formulate things there. So I will use a setting where you can talk about a lot of things. So let's call it this language called differential graded categories. So we are always over our base field. And we consider these objects, so these DG categories, so this curly A, so this is nothing but just an ordinary category, but it's enriched over complexes of K vector spaces. So the Hom spaces have a differential in particular. So examples. So if you have an algebra, a K algebra, or more generally the differential graded K algebra, then you have a corresponding DG category. DG category is a DG algebra with several objects. Also, if you have a scheme, then you can look at the perfect complexes on your scheme and consider a differential graded enhancement of that. And more generally, if you have an algebraic stack, you can look for similar things. So they all give rise to objects like this. Maybe here in stacks is too general. So since we are talking about orbifolds, a parenthesis in the particular case where the stack is this global orbifolds, then this thing, it is in fact just the G equivariant perfect complexes on X. So this is really the main object of study in this particular talk. Okay, so in here maybe just a remark. annotation. So I will denote by dgcat over the base field k. So this will stand just for this category of dg categories and dg filters. Okay, so it's a very large setting where you can fit geometry, you can fit non-commutative algebra, basically you can fit Fukaya categories, you can fit a lot of things. So there, now if you look at those K-theory and cyclical homology, I would like to really see what is the key ingredient that makes those decomposition works. And so the key property that they all share is the following. So this is what is called this additivity. So how to phrase it? So suppose that you just have a functor here towards an additive category. Let's call it D. So D, it's an additive category. And so you just ask for two properties. So first of all, you ask it to be Morita invariant in the derived sense. What do I mean by that? So suppose that you have a DG functor, if you want a morphism of algebras. And suppose that when you look at the corresponding derived categories, you consider the restriction along F, and that induces an equivalence. So this is somehow called a derived Morita equivalence. So so you want in this case that the invariant only depends on the underlying derived category in the sense that this F induces an isomorphism. So that's property number one. And property number two, it's really the word additivity. So one quick way to phrase it is as follows. So suppose that you have two DG categories. So if you want two algebras, and you have moreover a bimodule, a B bimodule, then from this data you can consider some kind of categorification of upper triangulated matrices. So you do construct a new DG category, which is just a disjoint union of A and B, and then in one direction the home spaces are given by the bimodule, and the other direction you just have 0. So it's some kind of upper triangulated matrix. And so what you ask for is that, well, A sits inside this category, B also, so you have, since you are going towards an additive setting, you can look at the direct sum of the image of A and B. You have an induced map, and you ask it to be an isomorphism. So in other words, this is just saying that your invariant does not see extensions. They treat all the extensions as a trivial one. So it's, in fact, it's pretty difficult to construct invariants which are not additive. So they must actually take into account the specific extensions, so kinds of all algebras and things like that. Yes, I agree. So this is the calligraphic B, and this is a math. So let's do like this to make a distinction. So examples of these things. So well, this is so general that a lot of invariants fit here, of course. And in particular, I want that the original invariants fit here.
Gonçalo, were you finishing the definition that such a functor is additive?
Yeah, it is saying that it has these two properties. Number one, that yeah, I said it by word, by talk saying, yeah, I didn't wrote it, but that's what it means. That property 1 holds, property 2 holds. Okay, so what are examples of these things? Well, again, algebraic K-theory satisfy these two properties. Cyclical homology satisfies these properties, and things with the more topological flavor, like topological O'Shield homology. So these things also are additive, and more generally, all kinds of variants that you might think about also have these properties. For instance, Y-balls, homotopy K-theory. Okay, so now I'm actually entering in the theorem, and now I have one green board of notations, and then the second green board is the theorem. Okay, so now I will explain these symbols. They will appear again. Okay, so this is a pretty dense green board, so I need a little bit more space. The size will become smaller. So orbifolds. So again, our base field, little k, our finite group of order n. Again, we always assume that the order of the group is invertible in the field, but we don't assume that k contains the nth roots of unity. What else? We have our smooth scheme, and our group is acting there, and so I have the corresponding global orbifold, and moreover I have an additive invariant So now what are actually the notations? So this symbol will stand for the set of all cyclic subgroups of G, and I will use this notation for up to conjugacy. So if I have a cyclic group, I can look at its normalizer. So I'll denote it like this. So this is the normalizer of sigma, the subgroup of G. I will denote by R of G. So this will stand for the representation ring of G. So finite dimensional k-linear representations of G. And then there is this phenomena, since I'm working with an additive invariant, if you have a G representation here, then if you look at the assignment, so you look at the corresponding class here and look at tensoring over K with this representation, so that gives you an action on the orbifold, and so that action bifunctorial to give you an action on that. So it turns out that you get an action of the representation ring in here. So that's a fact. And another thing that we need is this tilde that it was in the formula. So I think I can erase this without loss of information. So if we have now a cyclic subgroup, it turns out that the representation ring of the cyclic subgroup, if you invert the order of the group, it comes equipped with a canonical idempotent, which can be characterized as the maximal idempotent whose image under all the restrictions. So you can look at the representation ring of sigma, you can look at the restriction to the representation ring of sigma prime for every singular prime contained in sigma but different from sigma, and this is 0. So it is the idempotent, it exists with this, which is characterized by this property. Maybe this is too vague, so I will explain you. Well, I lost the color shock. It's okay, it's okay. So maybe, so I recall that I'm not assuming the roots of unity. So in the case, if K contains the nth roots of unity, then this idempotent is pretty easy to see. What is it? So here in this case, your representation ring using character theory, it's of this form. It's a group ring over the dual group. So now if you choose a generator of this group, so let's say that this group has order m. So this is of this form. And so it's T with Tm minus 1. And now you can rewrite this just using the cyclotomic polynomials. You can write this as the sum on J dividing m on sigma n. And here you have T. And then you mod out by the cyclotomic polynomials. So in this case where you actually have roots of unity, your piece, this idempotent is precisely the idempotent corresponding to the case where J is equal to M, so it's this largest piece. So basically you just keep the things that are induced from lower subgroups. And then whenever this representation ring is acting somewhere, let's say on a certain object O, I will denote by O tilde the corresponding image of this idempotent. Okay, so this is the notations. So now what is the theorem? So of course, in here, if you don't have roots of unity, you use Galois descent, right? You add roots of unity and define something above which is invariant under the Galois action. Okay, so what is the theorem? So now the theorem is a motivic formula. That's the way I like to think about it. It says the following. So we assume that our additive invariant is taking values in a setting which is where n is invertible, so the target is linear in this sense. So number one, so first of all, what can we say about the invariant of the orbifold? So it decomposes into a direct sum indexed on these cyclic subgroups up to conjugacy. And here you just consider these corresponding orbifolds using just cyclic subgroups. So here what's happening is that the representation ring of sigma is acting here. So I recall you that this 1 over n is invertible. So it's actually acting here. So you can take the tilde. And then there is also the normalizer of sigma, which is acting here and acting here by conjugacy. And so it still is going to act on this direct factor. So this first simplification is telling you that your invariant only depends on cyclic subgroups. That's the first reduction that you can always make. Yes, yes. I'm not, yeah, I forgot, yeah. When I meant additive category also in particular. It's a good point because it's being filmed, right? So so the board star, double star, and triple star contain all my possible assumptions. Sorry. So now, so this is still complicated. There is this tilde, this direct factor, there is this action. So how to simplify? So now roots of unity, so now it's an arithmetic statement. So if the base field contains n delta is the normalizer, it's there. So if it contains the nth root of unity, then in this case we can simplify so we can rewrite this as, so again, indexed on cyclic groups up to conjugacy. So now here you look at this fixed point data, and then you have this formula. So let me explain what this is. So this we already know what it is. So we have roots of unity, so it's actually this top component. This is a module over this. It's a projective module over this. This guy invariant is taking values in a category which is linear, so it makes sense to tensor over this thing with this module. So in particular, if this is free, I'm just doing a bunch of direct sum copies of this guy. And now in this thing, the normalizer still acts here, and still acts here by conjugacy. The conjugation. So. Okay, so if you have roots of unity, you have that simplification. So you somehow remove the tilde here. You place the complexity of the direct factor just in this piece. And now we can go further. So if not only you have roots of unity, but moreover, the target is not only linear, but it is L linear. It is L linear for a field L, which contains again the nth roots of unity, and moreover the order of the group is invertible in that field, then in that case we have a simple formula for the invariant of the orbifold, which is given by just you look at elements of your group up to conjugacy, you look at the value of the invariant on the G invariants, and then take the centralizer that is still acting there. So if you don't like to make choices, you can rewrite this in this way. And moreover, so there is still something to say here. Moreover, if your invariant it is lax symmetric monoidal, then these isomorphisms, they are actually isomorphisms of monoids. So so this is the main theorem. So let me come back to it. So very roughly it says that the invariant is completely controlled by the cyclic subgroups. If you have this arithmetic condition, you can simplify, put all the complexity in this piece. If moreover you have linearity on the target, then you have this extremely simple formula. It's kind of inertia formula for your invariant. And moreover, these things, if the invariant is monoidal, then the multiplications are well behaved. So now let's recover the formulas that we saw at the very beginning. So what are examples? So they respect. They are already an isomorphism, but the multiplication is is compatible under your map. If you multiply here and go here, it's the same as going here and then multiply here. So there is this thing is commutative. You can equip this with, so this is a stack, comes equipped with tensoring over this stack. That gives you a multiplication on this thing. On the right hand side, I let you guess what it is. So here it's the same story, and then this multiplication will descend on these factorizations, and I'll let you. It's basically only one possibility that you can. So algebraic K-theory. So how do we recover the formula of Vistoli? Well, you apply number 2. So number 2, K-theory, if you invert the order of the group, then you recover this formula. So this is the formula of Vistoli. So it is telling you that the formula of Vistoli, well, is using roots of unity, but the proof, the initial ingredient makes things work, is really additivity. So cyclic homology, and moreover, you can enhance this isomorphism to an isomorphism of spectra and things like that using this technology. In cyclic homology, well, you apply number 3. So cyclic homology is a theory which is linear on the target with the same linearity of the base field. So you get that the cyclic homology is this direct sum indexed by the elements of G of the cyclic homology of this fixed point data. So it turns out that for cyclic homology, you can actually remove the roots of unity assumption for this specific invariant, and moreover, since you are assuming that the order of the group is invertible, in the base field there is no difference between G invariants and G co-invariants, so you can rewrite this in this way, and so you get actually the Baranovsky's formula. So the inconvenience of using co-invariants is that they are badly behaved with respect to multiplicative structures.
Do you get, in fact, the same isomorphism?
Yes. The isomorphisms are what you expect. It's by pullback using the inclusions on the fixed data inside of X.
Do you use this co-invariance for a reason?
No, I think because yeah, I mean, so lots of people prefer this viewpoint, which is isomorphic, but this viewpoint allows you to keep track of the monadal structure, which is an improvement. Another invariant, of course, now we have, so far we have a unified proof that recovers both statements, but as usual now you would like it to get new statements. Yes? Say it again. Always. Say it again. Yes? I don't know. I don't think so. There is an issue about removing, for instance, the linearity of the target. And that would correspond, so in particular, let me say that the proof of the theorem, so what we do is that, so there is in particular a universal additive invariant. So if I want to prove this formula, I'll prove it there in that category, which is usually called this category of non-commutative motives. Turns out that that category has an explicit description in terms of K-theory, so we can reduce the result to a K-theory statement. Using technology, you can reduce it to Artin's induction theorem, which is the statement of K-theory when X is a point. This is just a result about representation rings, how the representation ring can be recovered. So if you remove this 1 over n, then you can try to do the same thing using Brouwer's induction theorem. In that case, you get a much more complicated form. Okay, so another invariant is periodic cyclic homology. why am I saying this? Because it's related to physics, so no number theory but physics. And it's related as follows. So let's say that we are over C. So I can apply periodic cyclic homology is one of those invariants. When I apply it to here, well, I get this formula. That's what the theorem tells me. So now I can do the same. So here I can put G downstairs. And then this, some people usually call this the orbifold cohomology of your singular geometric quotient. So it's in C. So I'm being too quick. Sorry for that. Jet lag. So periodic cyclic homology, since I'm in characteristic 0, and these things are smooth, this thing, it's in fact using the Urschel-Constant-Rosenberg theorem. This is isomorphic to the Ram cohomology. And since I'm over C, it's isomorphic to Betti cohomology, so you can actually rewrite this in terms of a direct sum of cohomology of this fixed point data over C, where the G is acting. And this, some people use this as definition of orbifold cohomology of this singular geometric quotient. So what is orbifold cohomology? Well, it's periodic cyclic homology of the orbifold. This? This or this? It is a star. This thing is Z2 graded. This thing is Z2 graded, so this thing is also Z2 graded. You put the even and odd parts here. Direct sum of the even and direct sum of the odd parts. Okay, so other things. So now we also have topological Urschel homology. So again, although topological, it also has some linearity, and so you also get some similar formula for the orbifold. So you get formulas like this for the THH of your orbifold. So these kind of formulas, if you look at the proof of Varanovsky and try to prove this by placing a T every time in the proof, I don't know how to do it. So, okay, so I don't know how to do this thing otherwise. And also other things, just to exemplify somehow number 3, to emphasize that my L doesn't necessarily need to have the same characteristic as K. So that's the last example. Too many examples. So what are good Willis for?
Well, we have a group acting. He thinks of an algebra, a group acting on a scheme, and then you take the direct sum over all of the elements of the group, and you get those with infinite orbits and those with finite orbits. But in your case, there's no infinite.
Yeah, there's no infinite. Yeah. So I think yes. Yeah. The particular case of a finite group. Yeah. So maybe the last one is topological periodic cyclic homology. So again, this is an additive invariant. And so now I'm in positive characteristic, a perfect field. I look at the corresponding ring of p-typical Wicht vectors and the corresponding fraction field. So this thing, it's a lax monoidal functor with values in here, in these Z2 graded vector spaces. So you actually get a formula for the TP of the orbifold like this. After inverting 1 over P. So you get an isomorphism of Z2 graded algebras over this fraction field. Okay, so there are a common proof and much more decompositions that hold, and the key ingredient is additivity. So now, so how much time do I have? About 20 minutes? So now, so we are decomposing the invariant. We can ask where does the decomposition occurs? Does it actually already occurs at the level of the category itself? So that's just a quick remark saying that that is not the case. It's something that is not occurring upstairs, only downstairs. And so the name, so I'm going just to erase everything. Okay, so but I think I'm going to erase everything because I actually have, I think, 3 or 4 blackboards, and so I'm done. Okay, so what is the remark I would like to make about the difference between, so maybe is that another way to phrase additivity is in terms of semi-orthogonal decompositions, those that are familiar with that, in the sense of Bondol or Loff, is saying that additive means that semi-orthogonal decompositions become just direct sums, so you don't see these extensions. So the remark, it's a Mackay correspondence. So I'm interested in the G-equivariant perfect complexes. So now let's say that we are it's algebraically closed, our field. Let's make an example. Suppose that the group is C2. Suppose that I have an abelian surface. And suppose that C2 is acting on my surface by this involution. Then it is classical. Then if you mod out by this action, you get a highly singular scheme. And however, this scheme admits a canonical crepant resolution given by the Kummer surface S, which is obtained by blowing up the 16 singular points downstairs. And so if you do the math, so the invariant of my G-equivariant thing, so the perfect complexes which are G-equivariant, the C2 equivariant perfect complexes on S, that's the same category as the category of perfect complexes on this scheme. So in your formula you can replace here by the Kummer. And if you do the computation of the theorem, it's telling you that this decomposes in 16 copies of the base field, plus you have the invariant on S and the C2 fixed points. So that's the first thing. The second thing is that if you look at this category of perfect complexes on the Kummer surface, so this thing, it's a Calabi-Yau, and it's connected. So this thing, since it's Calabi-Yau, does not contain any kind of semi-orthogonal decomposition that you might think about. So it's something highly indecomposable from the categorical viewpoint. So this thing has no semi-orthogonal decompositions. So you can rephrase additivity by saying whenever you have a semi-orthogonal decomposition, that becomes a direct sum. Here you don't have, it's highly connected. And however, when you go downstairs, you actually have a decomposition. So you cannot lift, of course, in general, these things. Okay, maybe now let's change a little bit the last 15 minutes, talk about conjectures. So 2 blackboards about conjectures. Okay, so I'm in characteristic 0, and I have a smooth proper K-scheme, and there are a lot of conjectures in the market. In particular, we have the standard conjectures of Grothendieck, so the sign conjecture and the conjecture of type D. So they are due to Grothendieck in the 60s. So this is telling you that the Kunet projector, the even Kunet projector is algebraic, is induced by a cycle. This is telling that there is no difference between homological and numerical equivalence relations. And then later there is a conjecture, which I call V, introduced by Voevodsky in the 90s. So he introduced a new equivalence relation on cycles, and he conjectured that that new equivalence relation is the same as numerical equivalence relation. So in particular, this conjecture implies Grothendieck's conjecture of type D. Well, what's the status of these things? Well, they remain widely open, so we know these things are true in low dimensions, for instance, in dimension below 2, dimensions below 4, dimensions below 2, and in these cases, moreover, for a billion varieties. So this, and there are more cases. There are more cases, but in general, is widely open. So this is due to Grothendieck, Kleiman, Lieberman, these thanks to Voevodsky and Claire-Voisin, for instance. Okay, so now what's the idea? I don't have a smooth proper scheme. I have an analog of that. So now let's say I introduce the following definition. So definition due to Kontsevich. So a DG category A is called, so you call it smooth. How do you phrase this? You simply say that when you look to it as a bimodule over itself, you ask it to be a compact object in this category, derived category of AA bimodules. So saying that I can resolve the diagonal in a finite number of steps. And proper by saying that when you fix two objects, you look at the cohomology, you ask this cohomology over K to be the dimension to be finite, and moreover that the total cohomology to be finite for any two objects. Okay, these are the correct notions in the sense they reflect the classical properties of smoothness and properness. A scheme is smooth and proper if and only if the perfect complex is smooth and proper. So now, if you have one of those, you can. So if you have a smooth proper DG category, so the analog of a smooth proper scheme, you can try to do the same story. So now I don't have cycles, I don't know what to do. This is a non-commutative algebra, but you have the Grothendieck ring, for instance. So I introduce the non-commutative analogs of those conjectures. So they have non-commutative analogs in the following sense. So the theorem, which is not of this talk, is a previous result that I have established. So if you have a scheme, there are two things you can do. You can look at the classical picture, or you can first look at its perfect complexes and then now consider this new conjecture. And you can do the same for all the others. So first of all, for this kind of completely general gadgets, we can formulate these conjectures. Second of all, when you pass from a scheme to perfect complexes, in general, you lose information, so you expect that you have implications like this. So if the classical conjecture holds, this one also, but the theorem is saying that also you have converse implication. So he's saying that these conjectures of Grothendieck and Vygotsky are actually conjectures in the non-commutative world. And also, in particular, I've used non-commutative technology to prove this right-hand side and consequently prove this in some new cases. So I already gave some talks on that. So today is a little bit different. Today is that this viewpoint, this theorem, allows you automatically, for instance, to extend the classical conjectures to stacks. So if you have a smooth proper K-stack, so then you can just do very quickly define the conjecture by defining as being the non-commutative version on this. So where this question mark is in here. So you can make this definition. So it's this conjecture for the perfect complex on your stack. And then the theorem is that, well, if the stack is something that you actually understand, so if you have a finite group acting on a smooth proper scheme, and then if you look at the corresponding global orbifold, then the conjecture, so the conjecture C, the sign conjecture for the orbifold, so these conjectures they actually hold when, again, whenever you're acting on something of low dimension, when the dimension is less than 2, dimension is less than 4, dimension is less than 2, and so independently the way you are acting. It's all about the underlying scheme that you are acting, and in this case, since the sign conjecture is stable under products, you can also add the case where you are acting on an abelian variety and the action is acting, so this acts by group automorphism. So these conjectures, they are stable under direct summands and things like that, so that you can actually so since we now completely understand the decomposition of these things, we can decompose the conjecture and reduce them to the classical ordinary case, which we know that it holds, so you can automatically bootstrap from there to the orbifold case. Okay, I still have time, but I think I'll stop. No, I don't know how to take hyperplanes and things like that. It doesn't mean that it doesn't exist, but I don't know how to phrase it.
In the last theorem, is it true that the conjectures on the left-hand side hold when all these fixed loci?
That's what's happening, exactly.
Okay, so it's actually stronger.
It is, absolutely. But since I don't have a control in which exactly kind of things, this will give you an immediate control in all the fixed point data, right? Absolutely.
So in the previous theorem, that this E of this orbifold is isomorphic to this direct sum. One recognizes that on the right-hand side is just the invariant of the underlying scheme of the inertia stack. So can you do you have results on this direction for non-global quotient?
I'm working on that. That's exactly the statement. So for instance, the analog of this cyclical homology statement for a stack would be that doesn't need the difference from the scheme and the inertia stack. You see, that's something that, as you see in the formula, that it's only the case when you have linearity on the target. Upstairs on K-theory, you have something much more complicated, which I don't know exactly how to phrase, just in terms of stacks.
You take a cyclic group of prime order, the subgroups, it looks like you don't need to invert the prime, the order, the end. Do you have examples that show that you need to? Or?
Why do I don't need?
Well, you're taking the direct sum overall of the cyclic subgroups, but there aren't any non-trivial ones. So you just have two terms.
Yeah, you mean in this example that I gave, the C2 action?
Yeah, so, let's take a simple group of order 2. The idempotents are pretty simple.
Yeah.
So you can formulate pretty much everything in it without inverting 2. Question is there exponent 2 torsion that you're worried about?
I mean, I don't know off the top of my head, but I think Artin's theorem fails if you haven't inverted the 2, for instance. I don't know an example on top of my head, but already in that baby version of the theorem, it fails. Yeah. In Serre's book, there is it's there. I can't read it.